through slides first.
We can just do it from the web here, right?
Yeah, we should be.
Yeah, so just pull up a browser.
Are you Google Docs?
Yeah.
Yeah, me too.
Okay.
goo.go.
Okay. G-O-O. G-O.
Slash E2, uppercase E. No, noun uppercase E. 9, T, uppercase D. No, lowercase t. I don't know if it actually matters.
Okay.
Go back to lowercase t, uppercase D, uppercase backspace, uppercase D.
Okay, got it. 2E9 TD. So there's no capital T.
Right. You're good. Sorry, that was too confusing.
No, that's fine.
Oh, we don't have internet.
We do. We have Hyatt conference. That's where we need to go. We say connect.
Oh, there's no internet connection on here.
But
Did you get it?
No, on this computer.
We should be able to connect to the Wi-Fi.
click the left mouse button, not the right one. Yes.
Are you even working on it?
We already have it.
Chicago 18, capital C.
Yeah.
Okay. Everybody else is breaking until 2 hours, just one.
I'll type that again.
We're connected, right?
Yep, yeah, you're on that.
Why does it say no internet access?
I might just have not refreshed. It should work. So you're on this web page now.
Okay. Let's try again.
How did you send it?
I just have it as a short link. I shared it with her also. Sweet. That's it.
So then I'm going to leave this open,
Yeah.
and then you can open it from here.
Perfect.
The others are actually on the computer.
Yours is the same. Yeah, open it. Just open it as a second tab. And
Should I just log in and
Did
do
you-
it, or?
Sorry?
oh, I just made it a public. I shared it as a public.
Yeah, me
thing.
too. But this long.
So then you can use a Google URL shortener.
Okay.
Just Google Google URL shortener, and you'll figure it out. It's pretty easy.
Yeah.
Are you? You're after me.
I'm last.
You're last.
Yeah, filling last minute for.
Sorry?
Who's first?
Anna-Leigh.
Anna-Leigh Brown. I'm going to introduce and then we can start.
I can't see how to do that on here.
What? What are you trying to do?
Shorten link?
No, it's done.
Do you have my talk on there?
Your talk? No, your talk is not on there. But we have time. Actually, no, we're going at the end of
Oh,
this.
here we go.
won't. Give me the link.
Google. G-O-G-L,
G-O-O.
like that. No, .gl, same as the other one.
.gl.
/ lowercase rd,
R-D.
capital A-N-Q-A.
A-N.
Q-A.
Q-A. There we go.
Yep, great.
So I'm going to leave this, both the tabs as it is, and
Yep.
then you guys can just do the slideshow.
Yep,
In the meantime,
perfect.
I can start with. Yes, I believe so. She should be. Is Anna-Leigh Brown here? Okay. All right, so let's get started with our oral sessions. Just a reminder, each speaker will be given 15 minutes, 12 minutes for the presentation, and then 3 minutes for questions. Please keep your questions at the end. That way the speaker is not interrupted in the middle of the presentation. We have 5 oral presentations for the first session. And we request absolute silence during the presentations, please. And with that, Anna-Leigh, take it away.
In advance.
And if you want, you can actually use that to present as well if you don't want to speak in this mic.
Oh, I think I can speak on the mic. All right, so today I'm going to be presenting to you my project looking at background mutation rate and selection in explaining the occurrence of cancer mutations. So one of the critical questions in cancer research today is that given that we see tons of different mutations, which ones are actually important for cancer progression and which ones are just irrelevant passenger mutations? So one easy rule of thumb for whether or not a mutation is important in driving cancer progression is that if the mutation occurs in more than one patient, then maybe that means it's important. However, mutations might occur in multiple patients not necessarily because they are important in cancer, but because they are particularly likely mutations. Take, for example, a C2T mutation in the context of CPG, which would be a C followed by a G in a 5' to 3' context. In mammals, most CPGs are methylated, and methylcytosine is a particularly likely and hypermutable thing because it is very easy for a deamination reaction to occur, resulting in cytosine to thymine mutations. However, we know that some mutations that reoccur are definitely important for cancer progression. Take, for example, BRAF V600E, which is one of the most prevalent amino acid mutations, which is caused by a single nucleotide substitution. This mutation is seen in over 40% of thyroid cancers and over 30% of melanomas. So the idea is if we have an idea of what mutations are likely and what mutations are unlikely to occur, that can help us understand which mutations are important for cancer progression. So building an accurate model of background mutation rate can help us identify mutations important. So if you build a background mutation rate of what you would expect to see and compare that to what you see in cancer, mutations that are happening more frequently than you would expect are potential driver mutations, so they're important mutations for cancer. Another thing we know is that trinucleotide context is actually one of the most important single factors in determining mutation rate for a single nucleotide. So this is a study in actually de novo mutations in autism, and they looked at a wide variety of genome features, and they found by an order of magnitude, the trinucleotide at the site was actually one of the most important factors for determining mutation rate. So the goal of my project was to build a background model of DNA mutability using trinucleotide context in order to find which mutations are actually important for driving cancer progression. In order to build that background mutability, we first took a sample set of about, that's kind of hard to see, 9,000 cancer samples from ICGC, TGCA, and the pediatric cancer genome, and we had a little over 1 million mutations. So first we built a per nucleotide mutation rate using a very simple frequentist probability, which is just the probability for a given nucleotide substitution to occur in a given context. So for example, a T to C mutation in the context of ATT. And this is simply the number of times that it occurred over the number of samples you have, over the number of times that trinucleotide happens in a human diploid. From then, we are able to build a context-specific codon substitution rate. So for example, this codon, which is a phenylalanine codon, in this specific context, these are all the possible single nucleotide substitutions that could occur in this codon. And if we wanted to get the probability for this specific phenylalanine to mutate to a leucine, we could take a mutation here happening in the first position, or these two mutations here happening in the third position. And to get the probability of this occurring, it is 1 minus the product of the sum of the mutually exclusive nucleotide substitutions. So from nucleotide substitutions, we move to codon-specific substitutions. As a first basic question, just to make sure if this mutability measure makes any sense at all, we wanted to ask if mutations are actually accumulating in proportion with their mutability. So we derived these measurements from 9,000 cancer samples, and we wanted to look at a completely different subset of cancer samples to say, okay, is your measure valid, or are those just weird cancer samples and your numbers are totally irrelevant and mean nothing? So what we did is we took about 9,000 patients from the Memorial Sloan Kettering Impact Study, which is a very large cancer study, and we looked at mutations in 520 cancer census genes. And the first thing we found is we compared mutations which were observed to those which were theoretically possible but not observed. And we found that mutations that were observed had a 2.5 times average higher mutability than those which were not observed. Secondly, I looked at whether or not mutations that had a higher background probability occurred more frequently in those patients. And again, you see, I didn't do a correlation, but it would be good, that more mutable mutations are indeed happening more frequently in this other set of cancer samples. So our background mutability rate is actually valid and can be applied to other cancer samples outside of the ones that we use to determine it. Next, I looked at how a gene's role in cancer might affect how mutations accumulate. So in cancer, you have two broad classes of genes. There are oncogenes, which cause cancer through gain-of-function mutations, and there are tumor suppressor genes, which cause cancer from loss-of-function mutations. So gene used to do something, it can no longer do that job, causes cancer. So what I did is I then binned mutations by either the gene's role in cancer or the frequency. And so this would be how many times it occurs in a patient. This is 0, 1, 2, or 3 or more in 12,000 samples from COSMIC, which is a large database of tumors. So first you see that nonsense mutations occur in proportion with their background mutability in both oncogenes and tumor suppressors. Nonsense mutations are mutations which introduce an early stop codon and cause the protein to be cut earlier than it should have been. So you see that for both, as the mutability of the mutation increases, it is observed in more people. So it seems that for some degree, mutability is driving reoccurrence. We also see that silent and missense mutations are also showing a similar pattern in tumor suppressor genes, with more mutable mutations occurring more often in different patients. However, once we look at oncogenes, we actually see a kind of interesting pattern where it is increasing, so 0, 1, 2, until you get to those which are highly reoccurrent. So it's the same mutation happening in 3 or more patients, and these are actually happening at relatively low background mutability rates. And this is also true in silent mutations. So these silent mutations are happening. This suggests that rather than background mutability be important for the reoccurrence, it's actually selection which is causing these mutations to occur again and again in cancer. So can mutability help us distinguish between passengers and drivers in cancer? In order to answer this, we found a benchmark set of experimentally validated non-neutral driver mutations and neutral passenger mutations in known cancer genes. So these are from 17 different genes, and whether the mutation is neutral or non-neutral has to do with that gene's role in cancer. So for BRCA2, for example, this is a gene which is involved, or the protein is involved in homology-directed repair. It was assessed on its ability to do homology-directed repair versus TP53, which its role tends to be more important in activating downstream genes, and these mutations were assessed in relevance to that. And we actually see an interesting phenomenon that these non-neutral driver mutations actually have a lower probability of occurring across these cancer genes. So they're actually happening at less likely mutable spots compared to passenger mutations. So that brings us back to this kind of question that I asked earlier. If a mutation is occurring in more than one patient, does that actually mean that it's important for cancer? So just as a hypothetical thought experiment, if a mutation happens 3 times in a cohort of 5 people, is that interesting? How about if it happens in a cohort of 7,000 people? Does that make it an interesting mutation? And what we did to kind of answer this question is we used the binomial probability. So the binomial probability says how many times does an event occur in the number of times you tested it, and you think the probability is happening at this. So we developed what we call our B-score, which is simply a probability of a mutation happening k times in n samples given the context-specific mutability. So I saw 3 phenylalanine to leucine mutations. I have that codon probability that I defined earlier, and I saw it in 500 tumor samples. So we compared this to highly trained and widely used machine learning methods, so Condell and Fathom, and you can see if you just look at the area under the curve that Fathom definitely outperforms. But if you look at Matthews correlation, which is a measure used for class imbalance data sets, you can see that we're actually performing just as well as FATH-HTM, which is a highly trained Markov model, and we're actually outperforming Condell, which is a consensus score. We looked at this in another data set, so I looked at this is a recent paper from 2018, I think it's in Cell, and this is 700 some mutations in 50 different cancer genes. They, of course, ran their own predictors, you can see here. And actually, the kind of startling thing here is, first of all, B-score is doing as well as the measure probably a very trained measure here. And you can actually see frequency is outperforming quite a few of their measures, which frequency is the number of times the mutation happened in cancer, and at the very least, if you make one of these methods to predict a driver versus a neutral, you should outperform frequency. So right now, what we actually have this implemented in a web server. So if you just Google mutagene, you will find it there. You can look at whether or not we would call it a driver, potential driver. These benchmarks are based off our validation set that I explained earlier. You can see the mutability of a particular mutation, how many times we saw it observed in a set of 9,000, I think, right now. We don't have the more recent cosmic update in there yet. Our paper is available on bioRxiv now, so if you want to Google it, I went way more into depth into background mutability in that paper. My poster is, of course, downstairs, and I will be giving it again on Sunday, so 8:32 if you want to come talk to me. Ideally, what you should remember from this talk, if you remember anything at all, is that mutability is an excellent measure of background mutation rate in cancer. It can explain the reoccurrence of many mutations in cancer, especially in tumor suppressor genes. In oncogenes, we see this important and interesting thing where we see kind of a U-shaped relationship, suggesting that while mutations that are frequently occurring have a low background mutability, selection is driving their reoccurrence. Driver mutations inherently have a lower background mutability than passenger mutations. Frequency is an extremely good predictor of driver status, and any method aiming to distinguish between drivers and passengers should at the very least outperform frequency. B-score improves on frequency by adjusting for a background mutation rate, and it allows you to scale with sample size. And we have a web server to explore mutational processes and investigate driver mutations in your own cancer data. These are my acknowledgements, my PI, Anna Panchenko, my lab mates, people who, this pointer is pointed at me, people who helped with conversation, and of course I'm at the NCBI, and the Oak Ridge Institute for Science and Education gave me funding. Thank you.
Any questions? So I have a question. So that was a really informative talk. Have you looked at like the mutability of mutations that co-occur together? So what is the probability that like these mutations occur together in like thousands of samples that you analyze?
So the question was, have we looked at the mutability of mutations that co-occur together? We haven't looked at that exactly yet. I know, for example, that some mutations in, for example, DNA repair make other mutations much more likely. So, for example, if you had certain mutations in polymerase epsilon, I think it is, you can even see actually if you look at the mutations that happen, like that's how you know, okay, polymerase epsilon is somehow broken down. Another one, you can look at mutagenic factors like ApoBec dysregulation. So ApoBec is, I can't remember exactly what it is now, I'm blanking on it. It's a deaminase that causes DNA damage. It attacks single-stranded DNA, and it's something that often gets dysregulated in cancer, and these tend to be very hypermutable. And there's very specific spots that are mutated by ApoBec dysregulation that make other mutations more likely. But that's not a mutation, it's a dysregulation. So we haven't looked into that precisely, like if mutation A makes mutation B more likely. I think at the single nucleotide level, it's not totally likely, but you would expect to see, like, if you had polymerase ETA damage, or if you had damage to DNA repair mechanisms, and you could see that you would see more mutations being more likely.
Thank you. Right.
Yep.
Can you say again how you showed that oncogene mutations occur less likely than they
Yes.
have if they weren't in the oncogene?
Oh no, it's not exactly that. So the question was, there are mutations less likely because they're happening in oncogenes? Or am I, okay. Yeah. So to go back to what this is actually trying to say, or what I'm trying to say here. So it's not necessarily, because if you think about oncogene versus tumor suppressor genes, it has more to do with the characteristic of how the mutations happen and the characteristic of the gene in cancer. So tumor suppressor genes tend to, you need both copies to get knocked out for there to be cancer happening. Whereas for oncogenes, they tend to be dominant effects, and they tend to be at very specific locations. So BRAF V600E, for example, it's that very specific amino acid substitution. So for that one, it's not necessarily, because when you look at like tumor suppressor genes and these nonsense mutations, they can happen at a range of spots, and they also have to happen more than twice. So they have to be inherently likely to happen. Whereas the things that are driving here is these very specific spots where very specifically mutations there and nowhere else cause cancer. Yes?
If you are training a background mutation rate basically on TCJ and ICGC and all those, and you mentioned earlier that the trinucleotide, the likelihood of certain patterns is more likely to appear based on certain mechanisms which are clearly cancer driven. Does it make sense to actually use to actually train an overall background model rather than having something more cancer specific? At the end, it will be driven by like what's the largest cancer type in that pool.
Yeah, so while I've talked about mostly pan-cancer, the question was if it makes sense to use pan-cancer, whereas the largest cancer cohort would drive what you would expect mutations to be like. Did I understand that question correctly? So I have presented on pan-cancer because our test sets are pan-cancer test sets because it's hard to make a cancer specific. However, I would recommend that if you wanted to look at this, you would use cancer specific. So this is cancer specific background models. And I would recommend using that because we do have it broken down by cancer specific because those are more accurate, right? The kinds of mutations you expect to see in skin cancer are vastly different than the kinds of mutations you would expect to see in lung cancer, for example. One problem is that we haven't removed anything like hypermutators. So if you had a hypermutator, like if you have 9,000 samples and one of your samples has 30 mutations and the other one has 10,000, obviously that 10,000 is going to be driving those to some various degrees. Hopefully not too much is kind of the hope. But yeah, as I said, it would be better to look at cancer-specific mechanisms, and we do provide the ability for you to do that. Anyone else? Okay. Thank you.
Okay, next.